Bismillahirrahmanirrahim and Assalamu alaikum dear students. Welcome to our next lecture. In today's lecture we are continuing the previous text that we are discussing about the multivariate methods for the classification and regression of our data. Today we will look at the multivariate classification. Let's say that we are given a data set X which belongs to real numbers R and it has the dimension D. Let's suppose that we are given a data set of iris flower data set which is available as a standard data set for machine learning algorithms, which consists of 4 attributes: sepal width, sepal length, petal width and petal length. So, all these 4 attributes are given in numerical form in the form of real numbers. So, this notation must be understandable for you. It says that X, an instance of the flower that is taken from the set of real numbers, and the dimension of real number is D. In this particular case of iris data set, this is 4. And class conditional density is given as this: probability of X given Ci are taken as normal density with these parameters, where n tells that this is a normal distribution, d tells the number of dimensions in the data, mu is the mean, and this is the set of variances. So, it is a multi-dimensional data set, so it will have multiple variances. For example, there would be one variance for sepal length, there would be another variance for sepal width, there would be another variance for petal length and another one for petal length and width. And similarly, there would be different 4 means for the population: one for the sepal length, one for petal length, one for sepal width, one for petal width. And the normal distribution, as we have seen in the previous slides, is given by this. We are very much familiar with this data, with this expression or this equation. While real data may not often be exactly multivariate normal, it is a useful approximation. What it says that whenever we have to solve a machine learning problem and we are concerned about the assumptions of the density of the data in hand, it is a better choice that we assume the data in hand is univariate or multivariate normal. One clear requirement is that the sample of a class should form a single group. If there are multiple groups, one should use a mixture model. So, what this group mean? It means that all the data that we have that must belong to one kind of distribution, it should not belong to another kind of distribution. For example, there may be, in case of mixture model, there may be some data which is normally distributed, and there may be another that may be, for example, Poisson distribution and so on. Example of multivariate classification. Let we have a data set which consists of 2 features, one is age, other is income. So, X belongs to age and income. In this particular case, any instance of this data set could be represented as this R. Now, guess what should be here? D, that should be here 2, because it is a 2-dimensional data, and Y is a type of car. As we have discussed in the previous slide, we would have 2 means, one for average and one for income. A vector of mean age and mean income of customers who buy car of type I. So, this expression tells that a vector of 2 means, mean age and mean income of, and this I says that of those people which buy car of type I. Mean this is something like this: probability of X given Xi. This is similar kind of thing, right? So, we know about the this is C. We know about the class of the car and we want to find the probability of the X, the coming instance, and here we know about the type of the car and we have the means related to that type. And here we can see that a variance matrix, whereas this variance matrix contains this covariance and this is the variance. right? 2 entries that form the covariance and 2 entries that form the variance. So, sigma I square variance of age with respect to age who buy a car of type I, and this sigma I2 square, for example, this could be sigma I1 square, this would be sigma I2 square, and sigma I12, that is a covariance of age and income of customers who buy car of type I. Again, I would recommend you people to try to understand the meaning of these notations. What this mean is, why this is a variance and why this is a variance and why this is a covariance, and how they are denoted. The discriminant function is given as the function that is used for the discrimination or the classification, that could be written as this, as we have previously seen this function. So, it has been reproduced here again. Assuming that probability of xc belongs to some normal distribution with these parameters, right. This is the discrimination function that we have taken from the previous slide, and we assume that if this belongs to some normal distribution, then we will place here the value of normal density, and by putting the value of normal density over here and evaluating it, we get this expression. We have proved this expression in the previous slides, so I am not going to rework it here again. Let the training set has k equal to k, which is greater than or equal to 2 classes, mean that there are 2 or more than 2 classes in our data set, and the data set could be represented as this, where x is the number of instance, is the total data set, and this x is a vector of features of instance t, and this is the class of instance t, right. For example, this x may represent age and income, and this represents the car that they buy, where RIT is equal to 1 if xt belongs to Ci and 0 otherwise. It is again the same thing that we have seen in the previous slides. We have defined this function ourselves, that the value of Ri in our data set would be 1 if the customer buys a car of type I, otherwise it would be 0. And estimates for these two parameters are found using maximum likelihood separately for each class. For example, for C of I, we have this expression that could give us the probability of that class, and the sample mean could be given with the help of this formula, and the estimate for the variance could be given with the help of this formula. By plugging the values into discriminant functions here that we have seen in the previous slide, this is the discriminant function that we have got here, and we are going to plug in the values of our estimate. For example, we will put the value of this over here, and the value of this mi would be placed here because it is going to represent this thing, and the value of this si would be placed over here, right. We have already proved these formulas in the previous lectures, so there is no need here to reproduce them or to reprove them. And by putting the values, we can see that how this comes up. This is the variance taken from here. You can see that we get this, right, this expression. So, we are going to work with this expression. Here we put the value of mi and si, right, and solve it. It defines a quadratic function which can also be written as this, right, and this function is derived from this expression by just assuming different quantities. For example, wi is equal to -1/2 si inverse. So, where this wi is written, this expression is written, we can write there as wi, and again here we can write here the wi, and similarly we produce the other things, whereas w0 is assumed like this. So it's an easy expression to work without. You just have to suppose this value equal to this and replace this expression with the help of this. So the discriminator function would get simplified as x transpose wix plus wi transpose x plus wi 0. So we have these three assumptions over here. Dimensionality reduction. The number of parameters to be estimated are k into d for the means and k into d plus 1 over 2 for the covariance matrices. It's interesting to know that as the number of features or the number of dimensions increases, the complexity of the model also gets increases. And we have discussed this fact. In that case, if there are k classes and there are d features, so this much k multiplied d we need to compute the means, and this much variances need to be computed. You are required to verify these figures. You can have, for example, 2 classes and you may have 4 features. So then see that whether these expressions are correct or not. If d features are large and sample data set is small, now it's interesting. If the number of features in our data set are large, for example, there are 10 features and the data set is small, for example, it contains only the 100 number of instances, Si may be singular and the inverse may not exist, or Si may be too small, the variance, right. In this case, Si will be unstable. Small changes in Si will result in large change in Si inverse. So what does this figure tell? This point tell? This point tells that if the number of features in our data set are large and the number of instances are small, then introduction of one instance with different kind of values would change the behavior of our model to a large extent. It would have a more effect. In other words, if we have, for example, here this and we introduce another instance with the small data set, it would have more effect on the classification or regression of this data set. But if we have this big data set and we have this small one instance, it would have little effect, right. In other words, the generalization of model with small data set can easily be affected with 1 or 2 instances, whereas the generalization of a model which is trained on a large data set is little affected by the new instance which has varying or differing values. I hope this point is clear to you people. For stable estimates on small samples, if we want to find the stable estimate on small samples, we decrease the dimensionality of the data. It means that we reduce d, and we redesign the feature extractor R and select subset of features or merge them to small amount. So the overall lesson of this slide is that if the number of features are large and the number of instances is small, our classifier would be unstable. To have a stable classifier, we need either to increase the sample sizes, the data set size, or to decrease the number of features. Another possibility is to pool the data and estimate a common covariance matrix for all classes, right. Try to find out that what is the correlation, what is the behavior among all the classes, right. In this case, the equal covariance matrices, if all the classes have same variance or somehow we transform them into a case where they produce the same variance, then we can neglect the variance term, all those terms which involve the variances. So we can, it's only based on variance, we can ignore it and we are left with this. So how this happens? In most of the cases, we normalize our data into a single scale. For example, we have age, and let's say that may range from 10 to 100. So it has one scale. We have income that may range from, let's say that 1000 to 100,000. Right. So it has a different scale, it has a different scale. We normalize them and we transform them into 0 to 1 range. Right. Transforming this would give more chances to our data to have the same kind of variances, similar type of variances. In that case, we can ignore this term and we need to work with only this term, including the prior. And even if the priors are equal, what it means that? It means that the probability of all classes are equal. The number of instances of all classes are equal. For example, if we look at that we have 3 types of cars. So car type 1 has, let's say that 50 instances, car type 2 has 50 instances, car type 3 has 50 instances. So all cars have same number of instances, mean that their priors are equal, and if the priors are equal, they would have similar effect on the computation of discriminated function. So we can easily remove them. For example, for class 1, right, it is adding, let's say that 0.2. For class 2, it's again adding 0.2. For class 3, it is adding 0.2. So this could be easily then ignored. Its effect would be it's a little bit, right. So we can remove it and we can make our model more simple. Here is a point that we called as balancing of data, right. There are multiple ways to balance the data. Number 1, first and foremost, the simplest way is to have the equal number of instances of each class in our data set, as we have seen in the case of cars. Another way is that we would have the weighting mechanism, right, that would make the priors equal. For example, if we have 2 probabilities, one is 0.5 and other is 0.3, this is instead of 0.5, think it as 0.7 and this is 0.3. We would multiply them with a number that would make it equal, right. Let's say that I multiply this 0.7 probability, a class which has the prior probability 0.7, I multiply it with 0.3, I will get a 0.21, and a class having the prior probability of 0.3, I multiply it with 0.7 and it would give me 0.21. Now I can see that their priors are equal. How I made their priors equal? Because I have multiplied them with some weights that I have found, right. And finding these weights is an interesting process. Even if the data set is not well balanced, we can get the better and balanced results. The numbers here, for example, here we have used a number 0.3 and here we have used a number 0.7. These are known as weights. So when we are making a prediction or regression with class this 1, for example, at the place of I write 1, so I would multiply this whole result with 0.3. And when I am doing the prediction or even training with second class data, with the data that contains the instances of second class, I would multiply it with 0.7. It will, this multiplication basically would make all the terms that we have here. So I am going to multiply it, for example, for the class 1 with 0.3, and for class 2 I would multiply it with 0.7, and it's easy that the priors have become equal, right. Even before applying the discriminator function, the data set that we have, we will multiply the probability of data set with these numbers, and in that case the prior would become equal, and when the priors are equal we can ignore them. The optimal decision rule is to assign input to the class whose means Mahalanobis distance to the input is the smallest. Right. Now, how the Mahalanobis distance comes up? This is the Mahalanobis distance formula. Right. I would recommend you people to go on internet and search that how the Mahalanobis distance formula is implemented for the multivariate data in Python, and try to run that for your data set. Now, we look at this figure. Here we can see that this line is our discriminator function, and these are the class distributions. In this class we can see that the number, the variances along x axis and y axis are different as compared to this, right. Their distributions are somehow different, but here the covariances may be arbitrary but shared by both classes. If covariances are shared by both classes, their variances along both dimensions becomes equal, and the variances become equal, then our analysis become easier. Here in this figure you can see that the log likelihood or the likelihoods are represented for the normally distributed data that could be given in this form. Here again you can consider that this is for x1 and this is for x2, right. In both way you can see that there is normal distribution, and the posterior probability using this prior probability likelihood and prior probabilities could be given like this. This is just a visualization for your understanding. Linear discriminant. Unequal priors shift the boundary towards the less likely class. It is another fact. If we have unequal priors of our classes, for example PCI, right, they shift the boundary towards the less likely class. Here you can see that this is a discriminator function, so its boundary is shifted toward the class which is less likely, away from the most likely class. In this case, the quadratic term, this which we have seen in the previous slide, cancels since it is common in all discriminants. The decision boundaries are linear, leading to the linear discriminant. So, this is the function that we have seen in the previous slide. This is, and these becomes linear functions, because the quadratic term, this, if this is removed, then the remaining thing is linear, because the quadrant, the higher power of the term is because of this term, and it has been removed. So, we are left with this one. Decision regions of such a linear classifier are convex, right. Here this is a convex figure shown, and this is a not convex figure shown. Okay. It would be a good idea that if you go and look at the definition of convex, what is a convex problem and what is a convex shape basically. Naïve Bayes classifier. If we assume all off diagonal of the covariances matrices to be 0, what does that mean? It means that, so here we can see that the entry on the diagonal are non-zero, whereas all the entries which are present on off diagonal are 0. Right. So, all crosses are zeros and all the sigmas are non-zeros. More simplification is possible. If this is the case, the problem becomes univariate. It is very interesting. Can you see that how it becomes univariate? Because there are no covariances, only the variances exist, and variance is between the same variable. right. When there is no covariance, it means that the problem is reduced only to estimate this parameter that could be calculated with the help of single feature, and every single feature's variance would be calculated separately to be plugged in into our model. Then this discriminator function could be written as this. Here you can see that we have used this only the variance instead of variance matrix. The term xjt minus mij has the effect of normalization and measures the distance in terms of standard deviations. Try to understand. Previously we have studied about z-score. Basically this is the z-score formula. As the covariances are 0, right, classes are hyper ellipsoidal and are axis aligned, right. If covariances are 0, so if we have two classes, both classes, you can see that this variance is axis aligned. It is aligned with the x-axis, and this variance is aligned with the y-axis. Similarly, here you can see that alignment among the x and y-axis. All classes have same diagonal covariance matrices, but variances are not equal, and you can see that variances along the x-axis is different as compared to variance along the y-axis. The number of parameter that we need to estimate here becomes kd for the means. For example, if we have d dimension, so we would have d variances, right. It would range from 1 to d, and for each variance we will have to find out the mean for each class. So we will have k into d means and d variances. The number of variances have been reduced now. Thus the complexity of S is reduced from this to this. S is the variance. So the variance matrix complexity, because you see that if we have this kind of stuff, its complexity is d square, right. That we have 3 features, so the complexity of this matrix would be 3 square. However, if this is reduced to this, so it has only 3 variances that need to be calculated, and its complexity has been reduced. Euclidean distance. Simplifying even further, if we assume that all variances to be equal, remember from first slide to till now we are just simplifying our assumptions. If we simplify the case that the variances along x-axis and y-axis are equal, the Mahalanobis distance reduces to Euclidean distance. Here you can see that the variances are same along both dimensions. In this case, if we have to find the distance of this point from this point, it could be easily find out with the help of Euclidean distance. But in some different case, for example, we have this kind of stuff, right, then finding the difference from this point to this point cannot be calculated with the help of simply Euclidean distance. Then we have to generalize it because it has multi-featured. The distribution is shaped spherically centered and around the mean vector mi, then S could be written as S2D and S of inverse could be written as this. The number of parameters in this case is k cross d for the means and 1 for S2, so S square basically. So the discriminator function which is given like this reduces to this form, right, and if for the time being we ignore it, this term becomes a Euclidean distance which is just normalized by this, right. Here you can see that it is just a Euclidean distance formula. Previously, we have said that Mahalanobis distance is a generalization of Euclidean distance, and simplification of Mahalanobis distance is Euclidean distance. Nearest mean classifier, right? This is the nearest mean classifier that we will be using in our coming lecture. So, you must understand it, and it would be again a good exercise if you implement this in Python. There are many implementations available on the internet, so you can find one and understand it, how it has been implemented. If the priors are equal, then equation reduces to, if these priors are equal, mean that there is no variance. So, we can ignore that, and we are come up with here with this. Now, the discriminator function assigns the class to input x which has least difference or distance, right. So, if there, for example, in our particular case we have classes of 3 types, cars of 3 types, 1 and 2 and 3. So, what it would do, this function would find the difference with the mean value of class 1 of new instance x, and then it would find a difference of x with the mean value of class 2, then it would find a difference of class x with the mean value of class 3, and the minimal distance among all those 3 would be the result of our discriminator function. If mean is considered as a reference point, ideal a prototype, it becomes a template for that class, and the process is known as template matching basically. This can be expressed as this. This is just expanded in this form, and which is further expanded in this form, right. I would suggest you people to find a Python implementation of this formula, which is very much simple, and you may have done this formula in your previous classes, even in school and college. So, you can easily implement this in a programming language. Nearest mean classifier, this is the formula that we have taken from the previous slide. The first term, this x transpose x, is shared in all discriminator functions and can be dropped, this one. So, gi of x is this, where wi is equal to mi and wi 0 is equal to this. So, we have made another simplification. In all means of for each class, they have similar norms. If there is a similar norm, then this term can also be ignored. We can ignore this term as well, wi 0. So, we are only left with this term. When the norms of mi are comparable, dot product can also be used as a similarity measure instead of the negative Euclidean distance. So, we can think of finding the best discriminant function as the task of finding the best distance function. So, till now we have seen that we made assumptions that if this is equal for all classes, this parameter is equal for all classes, then we can drop it, and if this parameter is equal for all classes, we can drop it, and so on. What it say? It mean that if we are given some data set, we will try, before applying the classification or the regression model, we will try to apply these assumptions on the data set. As I have said on the previous slide, we can transform different scale data on a same scale data. We can have the assumptions about the normality of the distribution and like other assumptions. As an exercise, you must take a data set and try to apply the assumptions that we have studied in these slides on that data set and see whether they work or not. Summary: instead of learning the discriminant function gix, learn the suitable distance function. That is very interesting. How? Because here again, if this was a discriminant function that was involving the probabilities, the prior probability and so on, if we make good assumptions and we transform data in some suitable form, So, we can come up with only a difference function, which is easy to implement and easy to compute. So, we get rid of the probabilities of the data. Learn the suitable distance function P d x1 x2 such that for any x1 x2 x3 where x1 and x2 belong to the same class and x1 x3 belong to two different classes, we would like to have the distance of two instances belonging to same class would be smaller as compared to distance of two classes belonging to two different classes, right. And here is a summary that we have studied till now. Assumptions: shared and hyperspheric, then we would have covariance matrix of this form and number of parameters required would be 1. If we have shared and axis aligned variances, then we would have this kind of stuff, right. All covariances would be 0 and all variances would be non-zero, mean the diagonal entries would be non-zero and all off diagonal entries would be 0. We would need d parameters. If there are shared variances and hyper ellipsoidal their shape is, we would have Si is equal to S, and we will have these variances Sij. So, the number of parameters that we will need would be equal to d into d plus 1 over 2. And if the variances are not shared and their shape is hyper ellipsoidal, then we would have this much number of parameters, right. Go back from the previous slide, look at the things again and try to understand. Tuning the complexity. Reducing the number of parameters. Previously we have seen that if there are number of parameters are high and the data set size is small, we need to reduce the number of parameters or we need to reduce the number of features. The table shows how the number of parameters of covariance matrices can be reduced. This table shows, right. You must be able to understand every point of this table. Trading off the comfort of a simple model with generality. By taking simplifying assumptions about the covariance matrix and decreasing the number of parameters to be estimated, bias is introduced. This point says that if we move toward the simplicity or we move toward the simple model, bias has more effect on that as compared to the complex model. If there is a complex model, bias would have little effect on that. So, in these two equations, you can see that this is a very simple model consisting of one feature or one variable. The effect of this bias is higher. However, if we look at this complex model which consists of 4 features, the effect of this bias would be smaller. The takeaway lesson is that as the model gets complex, the effect of bias or use of bias has little effect. However, if the model becomes more simpler, the effect of bias becomes more prominent. In other words, we can say that getting a simple model introduces a bias. So, that is the lesson from this point. If no such assumption is made and the matrices are arbitrary, the quadratic discriminant may have large variance on small data, right. What it means that this point we have already studied that if we have large number of features and we have small data set size, then introduction of one odd type of instance of data may introduce a large variance, may change the effect, may have more effect on the data or the performance of the model. This is the bias variance dilemma, right. Complex model, more variance, simple model, more bias. The ideal can depend upon the complexity of the problem and the amount of the data. For a small data set, even if the covariance matrices are different, it may better be to assume a shared covariance matrix. right, that each covariance of all the variables is a shared one. A single covariance matrix has fewer parameters, as we have seen in the previous slide. It can be estimated using more data instances of all classes, and this corresponds to using a linear discriminants. It means that if we can have these simplifications, or we can apply these simplifications on our data set, we can have a linear discriminant function or a distance function to classify them. Input normalization. For Euclidean distance to measure similarity, it is assumed that all variables have the same variance and they are independent. In many cases, all variables do not have same variance. So, for example, age and yearly income have neither same variable nor the independent. So, in that case, to use Euclidean distance formula, the inputs may be separately z-normalized in a pre-processing stage to have zero mean and unit variance, right. So, it is interesting that we always apply this kind of step on the pre-processing of our data, whether that data is a numeric data or it is a speech data or it is visual data like images or the videos. On the other hand, even if the variables are dependent, it may better be to assume them as they are independent and to use the Naïve based classifier for them, right. So, here we have another assumption. Regularized discriminant analysis, RDA. What is a regularization? Let me look at that. Approaches that reduce high variance to lower variance at the risk of increasing bias are known as regularization methods. A method that combines all these as special cases is called RDA. The assumptions that we have discussed in the previous slides, if those are combined and applied on our data, the method is known as RDA. For Gaussian parameters classification, covariance matrices can be written as this. If it is normally distributed, we can write the covariance matrices like this, right, where if alpha equal to beta is equal to 0, the classifier is quadratic. If alpha is 0 and beta is 1, the classifier is linear and the covariances matrices are shared. If alpha is 1 and beta is 0, the classifier is nearest mean classifier and covariance matrices are diagonal with this variance on the diagonal. In between these extremes, we get a whole variety of classifier where alpha, beta are optimized by cross validation. When the data set is small, Bayesian approach by defining priors on this and this are that use cross validation to choose the best of the 4 cases assigned in table, given in table, right. Again, if we have a small data set, then either we can apply the Bayesian approach or we can apply the cross validation to choose the best of the 4 cases given in the table, previous table, this one. Population's likelihood and posteriors. Here we have different kind of population likelihoods and posteriors. For example, if we have our data X, right, and we want to make assumptions about that, so what are the assumptions could be, what the assumptions could look like. Arbitrary covariance, that is like this given here, different cases of covariance matrices fitted to the same data lead to different boundaries, right. If we assume arbitrary covariances, you can see that this kind of discriminant function is there. If there are only diagonal covariances and of all diagonal covariances are 0, then we will have this kind of linear discriminant function that could easily discriminate 2 classes. And if there are shared covariances, then we will have this kind of stuff. And for equal covariances, we will have this kind of stuff. So, this is just a visualization of our data, that if their covariances are of this shape, how they look like. Discrete features. In some applications, discrete features are required which cannot be normalized. Previously, you remember that we have assumed that x belongs to R D, where it was a real number. However, there could be the chance that x belongs to N D with natural numbers. Let such data belong to a Bernoulli distribution, then if such data belongs to Bernoulli distribution, then we can have this formula, right? P xj is equal to 1 if class Ci is given. And for n independent unit trials, we could write them in the form of multiplication, and we have also seen this expression previously. The discriminator function is then given by, we know discriminator function is given by this formula, and we put the data density function over here. So, in this case we put this data density function in place of this. We come up with this expression now, which is a linear discriminator estimator for Pij, right? This is the Pij. So, it means that if we have discrete features, right, and we assume a Bernoulli distribution for them, then we can again have a linear discriminator function. In general cases, let us suppose that we have k classes, right. We define a new 0 1 dummy variable as this, right. It is same like that we have previously assumed about xt and rt. Let Pijk denote the probability that xj belong to class Ci takes value Vk, right. In that case, Pijk could be written as Pzjk is equal to 1. For example, the value of this variable would be 1 if Ci is given, right, and Ci is also equal to the class I. Pxj is equal to Vk given Ci. Okay? Try to understand this. Xj, this Zk is basically, we can say that it is the Xj, right. It would be only 1 if Xj is equal to Vk, mean the data that we are given is belongs to the class, right, that is K class, then it would be 1 if the class probability is given to us. If attributes are independent, then we can write them like this: the multiplication of probabilities, right, P I j k and z k. The discriminant function, we know about the discrimination function, that it is given by this, and we plug these values into this discriminant function, right, and we have applied the log. That is why these multiplications are converted into summations, and maximum likelihood estimator for the Pij is given by this. We are not going into detail of this, however, you must have the idea that how the discrete features are dealt with. Multivariate regression, the last topic of today's lecture. Multivariate linear regression is given as this: we have some regressor function and there is some error introduced in that. This is, it produces some true value RT for some xt instance, and we can write it in the form of parameters like this, right, where w0 plus w1 x1 t, because it is a linear function, so we can write it like this. Epsilon is assumed to be a normal with mean 0 and constant variance. Maximizing the likelihood is equivalent to minimizing the sum of squared error. So, try to understand this point. If we are going to maximize the likelihood, it means that we are going to minimize the difference. What is the likelihood? This is class 1, this is class 2, for example, this is class 3, and we have some value x. We want to maximize the likelihood of this instance with class 1. It means that we are making the probability higher for x to belongs to this class. It means that we are minimizing the error or the distance of x belonging to this class. So, this fact is said in this point. and this E, right. We want to maximize the likelihood, we want to minimize the error, and error is given with the help of this expression, which can be further given as this. The difference between RT and the predicted value, this is the prediction, R square. So, we want to minimize it. Error is given with the help of this expression, and likelihood is given with the help of this expression. Taking the derivative with respect to the parameters Wj, where j is equal to 0 to d, because we have a d-dimensional data, we get these normal equations. Which equations? These, right. So, this equation 1, equation 2, equation 3, and up to we will get d equations, right, because we have derivated them with respect to W1, W2 up to WD. And in matrix form we can write them like this, right. It is a simple, how can we transform those equations into these matrix forms? Then the normal equation can be written as x transpose x w is equal to xdr. We have previously seen that if we denote it with a, it as x and it as y, right. So, we can write a with as x t x and y as x t r, right. We can solve for the parameters as to find the w. Here we have, this is for example w. So, similarly we say that w is equal to a inverse of y. We put the value of a inverse, we put the value of w. So, this is the value of a inverse and this is the value of y. So, this is a inverse and y. So, this was today's lecture. I hope you got this lecture. See you next time in next lecture. Allah Hafiz.